Over the past decade, the hydrogen economy has evolved from an abstract vision of the future into one of the most aggressively pursued clean energy opportunities in the world. But as momentum grows, a deeper and more urgent question has emerged. What actually makes hydrogen affordable? It's a question that policymakers, investors, developers, and engineers are all now asking, because the future of hydrogen will not be determined by enthusiasm alone. It will be determined by cost. Whether hydrogen becomes a mainstream fuel or remains a niche solution depends on the industry achieving and sustaining a production cost around $2 per kilogram. And that price target pushes us directly into the debate between two major production pathways: electrolyzers powered by renewable energy, and SMRs, small modular nuclear reactors, designed to generate both electricity and heat. Instead of treating this as a technological battle, the real issue is understanding which option enables hydrogen to reach economic competitiveness across different regions, scale levels, and energy environments. Electrolyzers have become the symbol of green hydrogen's promise. Using renewable electricity from solar, wind, hydro, or geothermal energy, electrolyzers split water into hydrogen and oxygen. Modern electrolyzer technologies, PM, alkaline, AEM, and high-temperature SOEs, have made major advancements in efficiency, reliability, and cost. But even with these improvements, one thing remains constant. Electricity is the biggest cost driver. Producing 1 kilogram of hydrogen typically requires 50 to 55 kilowatt-hours of electricity. That means the price of power directly determines the economics of the final product. In markets where electricity prices remain high, green hydrogen becomes almost impossible to justify. If a developer pays 10 cents per kilowatt-hour for electricity, the cost of hydrogen already sits above $5 per kilogram, before any equipment or operational costs are even included. This is why global interest in green hydrogen is heavily concentrated in regions with extremely cheap renewable electricity. Places like Western Australia, Chile's Atacama Desert, the American Southwest, Morocco, and parts of the Middle East. The lower the electricity cost, the closer electrolyzers get to economically viable hydrogen. But there is another layer to the challenge. Renewable energy is intermittent. Solar production peaks in the middle of the day and drops to zero at night. Wind power can be strong one week, weak the next. Electrolyzers can operate flexibly, ramping up when electricity is cheap and cycling down when it's expensive or unavailable. But this flexibility comes with wear, efficiency losses, and complex operating strategies. In markets where renewable resources fluctuate significantly, electrolyzers rarely operate at full capacity over long periods. This leads to low capacity factors, essentially the percentage of time the system is producing hydrogen at its maximum potential. A project with a low capacity factor spreads its capital cost over fewer kilograms of hydrogen, raising overall production cost. Even with cheap electricity, variability can undermine scalability and economic predictability. This is where SMRs challenge the limitations of renewables. Small modular reactors, unlike solar and wind, provide constant, around-the-clock baseload energy. They are designed to be safer, smaller, and more flexible than traditional large nuclear plants. But the real advantage SMRs bring to hydrogen production is not just electricity, it's heat. Breaking the molecular bonds in water requires a significant amount of energy. When hydrogen is produced using purely electrical energy, electrolyzer systems must supply all of that energy themselves. But high-temperature nuclear reactors can deliver heat at several hundred degrees Celsius, dramatically reducing the electrical load required. High-temperature solid oxide electrolysis takes advantage of this, using heat to facilitate the chemical reaction. When electricity and heat are combined, the total energy requirement drops significantly. The result is far greater efficiency, which translates directly into lower cost. A high-temperature electrolysis system powered by an SMR can potentially deliver hydrogen far closer to the $2 target even in regions where electricity is not particularly cheap. SMRs also offer the benefit of a high capacity factor. Nuclear reactors generally operate at 90% or higher, meaning they produce hydrogen almost continuously. This stable output spreads CapEx over a larger, more predictable amount of hydrogen production, compared to a renewable-powered electrolyzer project that may operate only 40 to 50% of the time. For industries that require consistent volumes of hydrogen, such as steel production, ammonia plants, refineries, synthetic fuels, or maritime hubs, this reliability is extremely valuable. In these settings, hydrogen cannot simply be produced when the sun is shining. It needs to be produced every hour of every day. SMRs excel in precisely those conditions. Yet despite these advantages, SMRs are not automatically the more affordable option. Nuclear projects still face expensive permitting, long development timelines, regulatory complexity, and high initial capital expenditure. Even with modular construction, SMRs are not plug-and-play assets that can be deployed in months. Developers considering nuclear hydrogen face multi-year planning cycles, public scrutiny, and extensive financing requirements. By contrast, electrolyzer installations can often be developed in 1 to 3 years, depending on scale, permitting, and grid connections. For companies or governments seeking rapid hydrogen deployment, electrolyzers have the clear timing advantage. The speed at which green hydrogen projects can be executed is one of the reasons they dominate current global announcements. Another complexity lies in downstream infrastructure. Hydrogen production is only the first step. Once produced, hydrogen must be compressed, liquefied, stored, transported, or converted into ammonia or synthetic fuels. These downstream processes add cost and often determine the final delivered price of hydrogen. Many SMR-powered hydrogen facilities are designed specifically for on-site industrial use, meaning the hydrogen is consumed close to where it is produced. This reduces transport needs and therefore cost. In contrast, renewable-powered electrolyzer projects are often built in remote locations with ideal solar or wind conditions, far from the actual centers of hydrogen demand. Transporting hydrogen hundreds or thousands of miles can add significant overhead. In many cases, the location of the electrolyzer, not the electrolyzer technology itself, becomes the defining cost barrier. Still, electrolyzers offer something SMRs cannot match: system flexibility. Electrolyzers can instantly adjust to fluctuations in electricity prices. They can capture excess renewable energy that would otherwise be curtailed. They can serve dual roles as hydrogen producers and grid balancing assets. In power markets experiencing rapid renewable penetration, electrolyzers provide benefits that nuclear systems simply can't. They help stabilize grids, absorb excess power, and support decarbonization on both the electricity and industrial sides of the economy. This makes electrolyzers extremely attractive in markets undergoing rapid renewable expansion, such as Europe, the United States, China, India, and the MENA region. Ultimately, determining what makes hydrogen affordable requires considering all variables: electricity price, heat availability, project scale, load factor, geographic limitations, regulatory frameworks, supply chains, industrial integration, and long-term operational economics. There is no single winner. Instead, hydrogen affordability depends on aligning the production method with the right environment. In regions with abundant cheap solar and wind resources, electrolyzers will continue to dominate. In industrial zones where heat demand and 24/7 hydrogen production are essential, SMRs offer a strong advantage. In hybrid systems where nuclear provides a constant baseline and renewables supply additional power for peak hydrogen production, the combined approach could deliver some of the lowest hydrogen prices of all. Hydrogen affordability will be defined by system design, not technology preference. Developers must understand how to combine electricity, heat, efficiency, infrastructure, and operational strategy to minimize levelized cost. Hydrogen is not inherently expensive. It becomes expensive when misaligned with the energy system designed to produce it. The path to low-cost hydrogen lies in smart, location-specific project development based on rigorous techno-economic analysis. And that is exactly where ReneEnergy.com supports the market. Whether you are developing a hydrogen project, seeking visibility for your technology, designing a financial model, or looking for tools to accelerate your feasibility study, our team and digital platforms help hydrogen companies grow with greater clarity and confidence. To explore our consulting services, marketing capabilities, or H2 Hub modeling tools, and to get a personalized recommendation on what your hydrogen project actually needs, visit https://connect.reneenergy.com today and take the next step in your hydrogen journey.